So pictured here in the CHF Museum is a very young Dr. James Lovelock. Most people associate James Lovelock with the Gaia hypothesis, which is certainly the thing that he is most well known for and that he has spent the bulk of his life on. But what most people don't know is that a much younger James Lovelock, around the time that this picture was taken in the late 1950s, he was working as a researcher in a medical institute in the UK and was facing a very specific challenge that he was trying to overcome: how to deal with potential cellular damage to frozen blood samples. There was concern that blood samples frozen that they would want to use in future experiments wouldn't be accessible because the damage of the freezing and thawing process would make those cells unusable. But to determine that, they needed to detect trace levels of a chemical inside of the blood samples that would indicate this. Unfortunately, all of the equipment in Dr. Lovelock's lab was not suited for this sort of investigation. He just couldn't detect the trace levels that he needed. So James Lovelock, being James Lovelock, decided to just go ahead and invent his own detector. The result of that work was the electron capture detector. Lovelock's electron capture detector was not only amazingly successful in allowing him to continue the experiment that he was doing on the frozen blood samples, it also opened up for him an entirely different perspective on the world around him. Lovelock turned his analytical gaze outside and started looking at water samples in nearby streams, taking air samples from around his countryside, and eventually doing a very Beagle-esque voyage down the Atlantic and detecting trace amounts of ground-level ozone out in the middle of the Atlantic, far from any urban center where anyone had ever seen this sort of phenomenon. What's fascinating about Dr. Lovelock is this is a time in the late 1950s and early 1960s when not only is instrumentation changing the way in which we think about the world, we also have the development of new vocabularies such as biopersistence and bioaccumulation, concepts that are emerging out of Rachel Carson's observations of the natural world. These sorts of concepts unified are what really set the foundation for a 1970s, what's broadly termed in the United States an environmental revolution that not only saw vast regulatory changes, but also a breakthrough in the types of science that were happening. This is when Sherry Rowland and Mario Molina are starting to understand the fate of CFCs in the upper atmosphere and what it's doing to our ozone layer. This is when ecology starts to develop as a science. So there's a broader context that is deeply rooted in our instrumental and instrumentation-based understandings of the world. Suddenly, things like parts per million were no longer analytical categories. They were actually accessible quantities that we could detect routinely in our environment. And interestingly, the image that you see just to the diagonal of Dr. Lovelock is a citizen down in Louisiana taking a sample of the air around him. And it's a wonderful juxtaposition that lets us see the ways in which an instrumental breakthrough inside of a laboratory actually becomes a tool that can be in the hands of many people, other scientists, other citizens, and the ways in which the science percolates out to other communities.